is the most important piece. I think Microsoft Research is really a great place to connect theory and practice because we're constantly exposed to very difficult technical challenges from product teams. They're tackling very difficult problems. And we also have the luxury of stepping back and thinking deeply about the problem we're facing and thinking about what kind of new theory we want to develop, what new methodology we can develop to address those problems. I remember in early 2000 when Microsoft started doing web search, and we had a meeting with the dev manager who was actually in charge of architecting the web search system. And so we had a very interesting discussion. We talked about how we were doing research in distributed systems, how we have dealt with a lot of problems when servers fail. So you have to make sure that the whole service actually stay correct in face of all kinds of problems that you can see in a distributed system. I remember at that time we had Roy Levin, Leslie Lamport, a lot of colleagues, and we talked about protocols. And at the beginning, the manager basically said, "Oh yeah, I know it's complicated to deal with all these failures, but it's actually under control." and a couple months later, he came back and said, "Oh, there's so many corner cases. It's just beyond our capability of reasoning about the correctness, and we need the protocol that we were talking about." It's also interesting that when you develop those protocols, we tend to make some assumptions. We say, okay, we can tolerate a certain number of failures. And one question that general manager asked was, what would happen if we have more than that number of failures in the system, right? And from a practical point of view, you have to deal with those kind of situations. In theory, when you work on theory, then you can say, okay, let's make an assumption, and that's just under that assumption. So you see that there's a difference between theory and practice. The nice thing about working at Microsoft Research is you can actually get exposed to those real problems and keep you honest about what assumptions are reasonable, what assumptions are not reasonable, and then you think about what is the best way of solving those problems in a more general sense rather than just solving a particular problem.
Your work in networked computer systems is somewhat analogous to another passion of yours that I'm going to call networked human systems. In other words, your desire to build community among systems researchers. How do you go about that? I'm particularly interested in your Asia Pacific Systems Workshop and the results you've seen come out of that.
So I moved to Microsoft Research Asia in late 2008, and when I was in the United States, clearly there is a very strong system community, and over the years we also see that community sort of expanding into Europe. So the European system community sort of started the system workshop, and eventually it evolved into a conference called Eurosystem, very successful, and we see a lot of people getting into systems and networking because of the community, because of the influence of those conferences, and the workshop has been very successful in gathering momentum in the region. And so in 2010, the member was Chandra Thakkar and Rama Kotra, who were my colleagues at Microsoft Research, and they basically had this idea that maybe we should start something also in the Asia Pacific region. At that time I was already working in Beijing, and I thought this is also part of my obligation. So in 2010 we started the first Asia Pacific System Workshop, and it was a humble beginning. we had probably about 30 submissions and accepted probably a dozen. It was a good workshop, but it was a very humble beginning, as I said. But what happened after that was really beyond our expectation. It's like we just planted the seed, and the community sort of picked it up and go with it. And it's very satisfying to see that we're actually going to have the 10th workshop in Hangzhou in August. If you look at the organizing committee, they're really all world-class researchers from all over the world. It's not just from a particular region, but really all the experts across the world contributed to the success of this workshop over the last almost 10 years now. And the impact that this workshop has is actually pretty tremendous.
What would you attribute it to?
I think it's really, first of all, this is the natural trend, right? You go from the US, who was leading in system research, and then expanded to Europe, and it's just a natural trajectory to expand further to Asia Pacific, given a lot of technological advances are happening in Asia. And the other reason is because the community really come together. There are a lot of top system researchers that originally, just like me, came from Asia Pacific region, so we have a lot of incentives and commitment to give back.
Right.
And all those enthusiasm, passion, or the willingness to help young researchers in the region, and those actually contribute to the success of the workshop, in my view.
Well, you were recently involved in hosting another interesting workshop or conference, the Symposium on Operating Systems Principles, right? SOS?
SOS.
And this was in Shanghai in 2017. It's the premier conference for computer systems technology, and as I understand, it's about as hard to win the Big Four as the Olympics.
Yes, almost.
So why was it important to host this conference for you, and how do you think it will help broaden the reach of the systems community worldwide?
So SOS is one of the most important system conference, and traditionally it has been held in the US, and later on we started rotating into Europe. And it was really a very interesting journey that we went through. Along with Professor Haibo Chen, who is from Shanghai Jiao Tong University, we started pitching for having SSP in the Pacific region in 2011. It was like 6 years before we actually succeeded. We pitched 3 times. But overall, even for the first time, the community was very supportive in many ways. So they would be very careful to make sure that the first one is going to be a success. And in 2017, when Haibo and I opened the conference, I was actually very happy that I didn't have to be there to make another pitch. I was essentially opening the conference. And it was very successful in the sense that we had a record number of attendees, over 800 people. And we had almost the same number, if not a little bit more, from the US and Europe. And we had, many more people from the region, which was what we intended. And having a conference in Asia Pacific is actually very significant to the region. We're seeing more and more high quality work and papers in those conferences from the Asia Pacific region, from Korea, India, China, and many other countries. And I like to believe that what we've done sort of helped a little bit in those regards.
Let's talk about the broader topic of education for a minute. This is really, really important for the systems talent pipeline around the world.
3 days. It's a huge time commitment. But you see all the passion from those professors. They're really into improving teaching. They try to figure out how to make students more engaged, how to get them excited about systems, even how to design experiments, all those aspects. I'm very optimistic that with those passionate professors, we're going to see a very strong new generation of system researchers. And this is, I think, the kind of impact.
Before we get into specific work, I'd like you to talk about what you refer to as a fundamental shift in the way we need to design systems. And by we, I mean you. In the era of cloud computing and AI, you suggested that things have changed enough that the older methodologies and principles aren't valid anymore. So unpack that for us. What's changed, and what needs to happen to build next-gen systems?
Yeah, that's a great question. I'll continue with the story about building fault-tolerant systems. So in the last 30 years, we've been working on system reliability, and we've developed a lot of techniques, a lot of protocols, and we think it will solve all the problems. But if you look at how this thread of work started, it really started in the late 70s when we were looking at the reliability of airplanes and so on. Of course, there are assumptions we make about the kind of failures in those kind of systems, and we sort of generalize those protocols so that it can be applicable up until now. But if you look at the cloud, it's much more complicated in many dimensions, and the system also evolves very quickly. And a lot of assumptions we make actually start to break. And even though we have applied all these well-known techniques, that's just not enough. So that's one aspect. The other aspect is, it used to be that in a system we build, we can sort of understand how it works, right? And now the complexity has already gone beyond our own understanding. We can't reason about how the system behaves. On the other hand, we have seen a lot of advances in, for example, machine learning and deep learning. So one thing that we've been looking into is how we can leverage all those new technology in machine learning and deep learning and apply to deal with the complexity in systems. And that's another very fascinating area that we're looking into as well.
Well, let's get specific now. Another super interesting area of research deals with exceptions and failures in the cloud scale era, and how you're dealing with what you call gray failure. And you've also called it the gray swan, which I want you to explain are the Achilles heel of cloud scale systems. So how did you handle exceptions and failures in a somewhat less complex pre-cloud era? And what new methodologies are you trying to implement now?
Right. So as I mentioned, in older days, we are targeting those systems with assumptions about failures, right? Like crash failure, a component can fail. When it fails, it crashes. It stops working. And nowadays, we realize this kind of assumption no longer holds. So this is why we define a new type of failures called gray failures. So thinking about what kind of name to give to this very interesting new line of research that about black swan or gray rhino. Supposedly, because we're talking about the cloud, we want something not as heavy as rhino. We want something that can fly. And the reason we call it gray is because a system component is no longer just black or white. It could be in a weird state where, from some observers, it's actually behaving correctly, but from the others, it's actually not. And that turns out to be behind many of the issues, that major problems that we're seeing in the cloud. And it has sort of some components of black swan in the sense that some of the assumptions we're making breaks. So that's why everything we build on top of that assumption start to break down. So for example, when I mentioned the assumption about the failure, right? If you think that it either crashes or it's correct, then it's a very simple kind of world, right? But if it's not the case, then all the protocols that will work under that assumption will cease to work. It also has this connection with gray rhino, because gray rhino is this problem that everybody sort of sees coming, and it's a very major problem, but people tend to ignore it for the wrong reason. And in our case, we know that for the cloud, all those service disruptions happen all the time, and there are actually failures all over the places. It's just very hard to figure out which ones are important, but we know something big is going to happen at some point, right? So we try to use this notion of gray swan to describe this new line of thinking where we really think about failures that are not just crash failures, or not even debilitating failures where it's essentially arbitrary failures, but there's something in between that we should reason about, and then using those to reason about the correctness of the whole service.
So does the word catastrophic enter into this at all, or is it?
Yes, that could be catastrophic eventually.
How does that kind of thinking play into what you're doing?
If you look at the cloud system, it's like a rhino sort of charging towards you, and before it hits you, there are a lot of busts and noise and other things. But you just don't know when and how something bad is going to happen, right? It could be catastrophic. It happens actually a couple of times already. And so one of the things we try to do is to try to figure out when and how bad things can happen to prevent catastrophic failures from all the bust and maybe other signals we have in the system. There are signals, it's just we don't know how to manage them.
Part of your approach to coping with gray failures is a line of research you call cloud brain,
right.
And it's all about automatic troubleshooting for the cloud. It's actually a huge issue because of the remarkable complexity of the systems. So tell us how cloud brain, what you call DeepView, is actually helping operators, the people that have to deal with it on the ground, simplify how they write troubleshooting algorithms.
So I think cloud brain is one of the efforts that we have to deal with gray failures. And remember, we talked about the challenge that come from complexity of the system or the scale of the system. You would really have a huge number of components interacting with each other. But on the other hand, we can really leverage the scale of the system to help us in terms of diagnosis and detecting problems, even figure out where the problem is. And this is the premise of the Cloud Brain project. So it has actually three components, three ideas. The first one is really the notion of near real-time monitoring. And so instead of trying to look at the logs after the fact and then analyze what happened, we try to have a pulse on what the system is doing, how it's doing, and so on. So that's the first component. And the second component is we really want to form a global view. So it's not just one observation we make about the system, but really observations for all over the systems combined, so we can actually understand how the system is behaving and which part is actually having a problem. And then the third part is once we have all these global observations that come in real time, then we can use statistical methods to really reason about what's abnormal and so on. So this is where we really leverage the scale, the huge amount of data. That used to be a challenge, and now becomes an opportunity for us to actually come up with new solutions to handle the complexity of the system.
So how does that help an operator simplify writing an algorithm?
Right, so now the operator actually has all the data in real time, and you can write this very simple algorithm that operates on the data, sort of like a SQL query, right? And then you can emit signals and tell people that something's wrong or something's correct, or maybe we have to pay attention to part of the system that seem to have some problems.
So where is this great failure research with all its pieces and parts in the pipeline for production?
Overall, we are not at the stage where we solve all the problems, but we have pieces of the technology we developed to solve some specific problems, like DeepView and CloudBrain are the two projects that have already been incorporated in Azure to deal with network-related problems, for example. But we're far from solving the problem. It's really sort of a research agenda that we set out probably for years to come. And one idea that we've been working on, which is actually very interesting, is that we really have to change how we view programs. In the past, for defensive programming, we have been trained to handle exceptions. And it turns out that handling exceptions in a large complex system is not enough. So one of the ideas that we've been thinking about is changing exception handling into exception or error reporting. So you start to collect all those signals that we talk about, the dust when the rhino comes charging at you. So you have to really collect those dust towards one place so that you can actually reason about the behavior of the system. And that's one of those major shifts that we see coming in how we develop systems, not just after the fact. We already have this beast and now we need to understand what's going on. So those methodology, I think, is where we're pushing. It's not just solving a specific problem. We have an incident, we try to solve this problem, we can do that. But more importantly, this goes back to the theory of needs practice. So we need to come out of looking at the specific instances, but think about what methodology we should adopt to change the status completely.
So how do you implement then a brand new thing? I mean, we talk about the beast that already exists and is growing. What are you proposing with your research?
Right, so this is all the hard problem. We already have something running and it has to keep running, and now it has all the problems we need to solve. So one of the ways we deal with those challenges is trying to solve the current problems, like CloudBrain and DeepView sort of try to fit into the current practice. But for some other projects, what we do is, like what I talked about, changing from exception handling to error reporting. That actually is a system we built that we can transform automatically a piece of code that does error handling in the traditional way into a piece of code that actually does error reporting in the way that we desire.
Right.
And that helps because we don't want everybody to rewrite the whole code base. It's just not possible. So we have to find ways to help developers to sort of do the transformation and also live with the current boundary of the system, and we hopefully gradually will move towards the right direction.
And I think you see that in just about every place software exists. If there's a legacy system, you've got to retrofit some stuff that added complexity to it.
That's right.
But you can't just make everyone throw out what they're already using. So this is a big challenge. I'm glad you're on the job. Well, we talked about what gets you up in the morning and all the work you're doing to make sure that everything goes right. That is basically what you're doing, is trying to make everything go right.
Right.
But as you know more than I know, something always goes wrong.
Right, unfortunately.
So I know. So given what you see in your work every day, is there anything that keeps you up at night?
Yes, I think we're realizing that the kind of distributed system we're designing or building are becoming more and more important. They're becoming part of the sort of critical infrastructure of our society. And that puts a lot of burden on us to make sure that whatever we're building can be mission critical.
Right.
And we have a lot of researchers working on formal methods, verification, just to make sure that the core of the system can be verifiable, to give some assurance that it's actually working correctly. And when we talked about applying machine learning, deep learning mechanism, but it's statistical. So sometimes, it's actually naturally there are cases where it breaks. So how we can safeguard this kind of system from what you call catastrophic issues. And this is also another thing that we have been putting a lot of thoughts into. And we're not short of challenges, especially on making the cloud infrastructure really mission critical.
Lidong, tell us your story. How did you end up at Microsoft Research, and how did you develop your path to the positions you hold right now?
Yeah, looking back, I remember when I finished my PhD, I started job hunting and I got a couple of offers, and I talked to my advisor. Of course, that's what you do when you're a graduate student. And he basically gave me a very simple piece of advice. He basically said, well, just go where you can find the best colleagues, the colleagues with maybe doing what